Okay, thank you, Juan. Today I'm going to share you about the LC lens for 3D technologies, and my name is Yi Pai Huang, and there is part of the works that we collaborated with Professor Manuel Martinez and Professor Baram Javili. So I think that many knows that there has several types of liquid crystal lens already been proposed. And first, the liquid crystal lens was proposed in 1979 by Professor Sato. 2004, Professor F.T. Wu summarized those liquid crystal lenses into different types. The first one is inhomogeneous liquid crystal lens, which the cell inside of the liquid crystal lens is inhomogeneous, which has the real lens shape and inject the liquid crystal inside. So when you switch the voltage on and off, the liquid crystal will be horizontally or vertically aligned. That can change the refractive index to be focused or non-focused. It's homogeneous liquid crystal, which means that the liquid crystal itself is homogeneous, but they use the field polymer and control voltage difference, the distribution, to make the liquid crystal itself has gradiently changed the distributions that can be formed as a green lens and to have the focus ability. The third one is electric field driven. We call it ELC, liquid crystal lens or lenticular lens, which is mostly commonly used on 3D stereoscopic display, which is the electric. We are at this side and use the fringing field to form the gradiently distribution of the liquid crystal molecule to focus. And when it's off, the liquid crystal molecule will be homogeneously distributed. That will be 2D, which is not focused. And the last one is the polarization active micro lens, which the liquid crystal itself is a fixed refringent lens, but they use a TN or some of the polarization switched cell that to switch the polarization from the perpendicular to the parallel polarization. And the polarization is parallel to the birefringent liquid crystal lens. It will be focused. On the other hand, it will be defocused. So that's the basic 4 types of liquid crystal lens. And the liquid lens that had been fabricated into various shapes of the array type. It can be circular, squared, hexagonal, or it can be lenticular, which means the shape, the profile of the liquid crystal lens is spherical or parabolic, or it can be Fresnel lens type that's used the discrete electrodes that can form the Fresnel lenses. And here are some publications that describe these different shapes of the liquid crystal lens array. And so you can use the liquid crystal lens or liquid crystal lens arrays for several different applications. One application is for 3D capturing. That's we use the actually distributed sensing technologies. Here you can see has a liquid crystal lens, and you change the focus. That can change the focus point of the object. And by using the actual distributed sensing technology, we can form the different edges, sharpness of the image that can know the 3D depths of the images. And you also use it for the tunable LC lens for a microscope that you can see. We can have the multi-focus and without using any mechanical movement, and can form the can see the difference of the microscope images. And only use a big liquid crystal lens. You can also use liquid crystal lens array for 3D capturing. Here you can see by using different frequency operation, you can change focus of the liquid crystal lens from 3.5 millimeter to 2.7 millimeters. And when you put a liquid crystal lens array in front of the sensor, which you can use the live field 3D capturing technologies, that when you change the focus of the liquid crystal lens array, you can expand the DOF, which, as the Professor Vidi and Professor Honghua mentioned, that you can extend the DOF. You see the right hand side of the two images, videos. This one is with fixed lens. So when we want to focus on the rear leg, it cannot be focused. But you use the liquid crystal lens array, you change the focus on the front leg, and you change the focus to the rear leg, that both of them can be clearly focused. That the DF can be extended from 100 micron to 950 microns. And also use liquid crystal lens array for some 3D endoscope applications. And it can be switched between 2D lens and 3D lens, and you can form a 3D shape. Carrying, that's of course the liquid crystal has been widely used for 3D display. It had been used for not only 2D and 3D switch, it also can be used for 3D rotatable, which means that when you try to rotate the mobile phone from vertical to a horizontal direction, both of them can be shown in 3D. And now 3D localizable with that we can only display the image in 3D, but the rest of the text could be in 2D. And also developed the technology to have this kind of 3D floating by using the integral imaging technologies. So you can see the 3D shows in here is like a floated up on the screen. And we also use it as a kind of animation. You can see the King Kong is a kind of standing on the screen and have this a little bit floating images. And we try to refocus at the front and the background. So now focus on the background, and you can focus on the foreground and for the background again. So you can see that it really has some depth information by using the lenticular the integral image with the liquid crystal lens. Of course, integral imaging of liquid crystal lens, it always has the low resolution, or we call it multi-phase phenomenon. So that's the image will have this kind of discrete or segment effect. That's use the liquid crystal lens, and we can, as Professor Javidi mentioned at the beginning, we can have the scanning moving of the liquid crystal lenses, dynamically integral images. With the two perpendicular liquid crystal lens scanned together, we can improve the resolution and also this multi-phase phenomenon that can smooth the edge of the integral image. Some other groups using the switchable liquid crystal lens for augmented reality goggle, like in Professor Yixin Lin, they also propose to use liquid crystal lens in here, and they can switch the focal length that can change the focal plane from the far scene to near scene. And also you can use the polarization switch the polarized that's reflected by the PBS and to the display panel and back to the camera, and you switch the polarization to the other directions that can go through the PBS and reflected by the other panel and back to the human eyes. So these two distance of the blue and red patch are different, and so that can have a different focus. So you can see in here blue, and the red part is blurred, and when you focus on the red part, the blue part are blurred. So that's also is a kind of applications by using liquid crystal lens for augmented reality goggle. And we'll combine this liquid crystal lens array as a kind of images in the virtual reality goggle. So we have the 3D integral images in here. So when this liquid crystal lens also can be switched on and off. When you switch on, it forms a live field 3D images. When you switch off, it's full resolution 2D images. So we quickly switch between 2D and 3D, which is 120 hertz switching. So the observer can see the depth information by using this live field 3D images, and also can see the high resolution of this 2D information. And this is the reconstruct images. You can see the 3 cube and also this pyramid that's can have this test sections by using this liquid crystal lens array. The final patch that we announced that a lot of applications of using liquid crystal lens for 3Ds, but they still have a lot of challenges. The first one is lens profile control. It's not easy to control a perfect lens profile of this liquid crystal lens. So focus point of the focusing point spread function is not as good as the fixed lens. So that will affect some of the crosstalk or MTF effect. And the second one is of optical performance, especially for the augmented reality or virtual reality. Usually the AR and the VR display, it has large field of view. So for large field of view, it will induce some of the off-axis optics. And off-axis distortion in the liquid crystal lens array currently is still one of the issues that will limit the field of view. And third thing of the liquid crystal lens is that the delta N is not high enough. So that's when you have the smaller delta N, you will have the small numerical aperture, which means that you will have the longer focus distance. When you have a long focal length, that will increase the total thickness. That's also affects the applications when you use it on the AR or VR applications. And the fourth, response time. The response time currently, if you only use for the switching, 2D, 3D switching, that's applicable because most of the liquid crystal lens cell gap is roughly about 15 to 60 micron, which will result in the response time about 200 milliseconds. That's applicable for 2D and 3D switching. But if the scanning or changing the focusing dynamically, it still needs to be improved. And the possible solution is to find the fast response liquid crystal material, and which that have been written in many research institutes or the companies like Merck. And the last issue is the polarization dependence. We know that liquid crystal is a kind of birefringent material. If you want to use for the liquid crystal panel, originally the display panel has polarization, that will be fine. But if you want to use it for augmented realities or some capturing applications, you need to put a polarizer in front of the liquid crystal lens, will decrease the transmittance. So that's also one of the issues if you want to use it for some of the special applications. So this is all of my today's sharing, and thank you for your attention. Thank you.